Yes, we are able to see the shared screen.
Hello.
Yes, Nitin.
Hello and welcome everyone. I'm very good afternoon to all. My name is Nitin Jangid and today me and my colleagues are going to present you all about the superconductivity. So first of all, going with the superconductivity, we should recall first what are the conductors, superconductors, and then we will jump to the superconductivity. Conductors. We all know what are the conductors. We have studied in our early stages of the classes. So first we will recall all the things. A material or the object that permits the electric current to flow easily. That means any material or any object that allows the electric current to flow in through it, it is known as conductor. How it is conducting easily the electric current? Because of the free electrons on its surface. On the topmost here there are given some good solid conductors like nail, wire, paper clip and scissors and pencil lids, and some liquid conductors are also there such as drinking water, lemon juice and milk and mercury. Now we also know the applications of the conductor in house electrical wiring or transmission line. Let's us see some application. The mercury is common material in the thermometer to check the temperature of the body. This is the one of the use of the conductors. And another one is a plate of a iron that made up of the steel to absorb the heat briskly. The aluminium also is used for making the aluminium foil to store the foods. Iron is also used in the vehicle engine manufacturing. So we all are knowing about the conductors. So going further, there are superconductors. Now, what are superconductors? A superconductor has a characteristic that the resistance can drop easily to the zero, almost zero resistance. So why the superconductor we are needed for? Because in conductors we know one property is there, so is resistance. So what happens in resistance actually? The power equals to I square R, where R is the resistance. So we can directly say that the power is directly proportional to the resistance. So what does the resistance do? Resistance actually opposes the flow of the current. So due to which there is a heavy loss of the current when we are using the conductors, simple conductors. So here comes the superconductor. What superconductor will do? Superconductor will reduce the resistivity rate, and so the power will use sufficiently. So the superconductors are the material having almost zero resistivity and before behave as a dimagnetic below the conducting transmitting transisting temperature. Unlike the familiar conductors such as copper and steel, the superconductor can carry a, a current indefinitely without losing energy. The superconductor will help us to carry the current without losing any energy. This should be note. So when now what are the superconductors and semiconductors different? You might be confused a little bit what is semiconductor and superconductor difference. So basically a semiconductor, the conductivity of the semiconductor is between conductors and insulator. So what is a conductivity? Conductivity is a ability of a material to carry the electric current. So the semiconductor's conductivity is between conductors and insulator, where in superconductor it is highly compared to the conductors. Coming to the 0.25 and 2.5 electron volt in between the semiconductors are there, where the superconductor is about 2.5 electron volt. Some examples of semiconductor are silicon, germanium, selenium, tellurium, and gallium arsenide, where the superconductors are aluminum, niobium, and magnesium and dibromide, etc. So this is a basic difference between semiconductor and superconductors. Wait a second.
Okay, Nitin.
Okay. Now superconductivity. The superconductivity is nothing but a property of superconductors. So a superconductivity is a phenomena in which certain metal, alloys, and the ceramic conducts electricity without resistance when it is cooled below a certain temperature is called as critical temperature. So here what is happening, the when we cool down the superconductors to a certain temperature, it shows a property which is known as superconductivity. So if we see the graph here, the green line is of superconductors and purple line shows for the normal conductors. So put when we seeing the purple line, when we decrease its temperature and its electrical resistivity also decreasing simultaneously. If we see by decreasing the electrical resistivity also decreases. But when the temperature comes to zero, the resistivity remains a bit there. Means there is a bit resistance left. But when we see the superconductors, the temperature and the resistivity simultaneously comes down, but at a certain point, the resistivity falls down very suddenly. So this is the different thing about the superconductors and normal metals. So at a very low temperature, in many conductors, the electrical resistivity is disappeared completely due to the fact that the electrons responsible for the conductors undergo a collective transition to an unordered state called as superconducting state. Practically, the superconductors are not having exactly zero electrical resistance. Also, only zero resistivity is not only the property of property dislining the superconductivity. So this property of cooling down is not only the property which shows the superconductivity, the metal is a superconductivity, but it also shows that there should be a complete magnetism in the superconducting state. The dimagnetism means here the magnetic flux does not exist within the body of the material. So how this superconductivity came into exist? So the Dutch physics High Kamerlingh Ons in 1911 founded the superconductivity. He had performed an experiment by taking the mercury as its material. When he was observing, he observed that when he was reducing its temperature and he was reducing the temperature of the mercury, the resistivity of the mercury also decreases simultaneously. But at a certain point, when the temperature was 4.2 K, the resistivity dropped very suddenly. And this clicks him to be a challenge of the point. So the Owens felt that the cold wire resistance would dissipate this suggests that there would be a steady decrease in the electrical resistance, allowing for the better conduction of the electricity. When it suddenly decreases its temperature, the resistivity also comes in the simultaneously. So this was happening due to the mercury was showing the mm, superconductivity property. The owns passed through a very pure mercury wire and measured it as steadily lowered the temperature. Much to his surprise, there was no resistance at 4.2. If there was a zero temperature at 4.2 when he was performing the experiment. So coming on forward, the how cold should be the temperature so that the superconductors convert into superconductivity. Till now, we can say that the superconductivity is a flow of electric current without resistance in a certain metal, alloys, and ceramic at the temperature near the absolute zero, and in some case at the temperature hundreds of the degree above the absolute minus 70 degree Celsius Kelvin. So how much is minus 70 degree Kelvin? If we see the ice is about 273.15 Kelvin, whereas we come to the dry ice, it is about 194.95 Kelvin. Now, if we say liquid nitrogen, nitrogen is 77.15 degree Kelvin, and we have to use liquid helium for this experiment, which is 4.04 degree Kelvin, and it is a very cold temperature. If we see in this picture, the liquid helium photo is there, and here it is written the caution. It is just because if you will use this liquid helium, if you are trying to take it in your hand, your nerves will directly be not working. Your body will stop working if you take it in your hand. So it is very dangerous at this point of temperature. So what is the applications and the future of this superconductivity? The superconductivity is still an exciting field of discovery since it was founded out in 1911, but still there is a technological application still now also, and it is a future. The superconducting magnets are some of the most powerful electromagnetic known. There are, it is used in MRI machine and NMR machine. So why we are using it in NMR and MRI machine? Why we are using MRI machine? We can use also the X-ray machine, but here the MRI machine is used to detect the disease which is in your liver or something, pancreas and etc. But the X-ray will be helpful for your bone fracture and that all. But the MRI machine will be useful to you in this in the cancer patients and etc. The mass spectrometer and the beam steering magnets used in the particle accelerators. The digital circuit based on a rapid single flux quantum technology and RF and the microwave filters for the mobile phone base station. It can be used here also. Coming on the further promising future of the application, the high performance smart grid, the electric power transmission, transformation, power storage device, electric motor, nanotubes, maglev trains. This is a maglev trains, which are the promising future applications of the superconductivity. If you will see here in the maglev train, there is a no contact with the floor or anything. So it helps in the zero resistivity and there is no act of friction in this. So it will help the train to cross its and approach towards its maximum speed. And if there is something future, some are the like cost, temperature, and capacity are the future concerns about the superconductivity, which take it to the how it will be useful or it is applicable for in the future. Now, for better understanding, I have one video. I will show that in the next slide. I think the audio is not coming.
When you share the screen, you have to do something with audio setting. You stop sharing, you retry for sharing, and while sharing, there would be some audio related option. Please check it out. You first of all, you stop sharing. Now you do it again.
This episode was made possible by the Vsauce 3 page.
Yes, done.
This episode was made possible by the Vsauce 3 Patreon. To support Vsauce. Vsauce. I'm Jake, and nitrogen is a gas until it gets really cold. Then it turns into this. Liquid. In this state, it has a temperature around minus 196 degrees Celsius. And these drops that are shooting off trailing vapor, well, they're literally boiling away into nitrogen gas at room temperature. And because nitrogen has a high evaporation expansion ratio, each drop expands to 700 times its volume in gas, even though it was just a tiny drop. Using a thermal camera, we can see just how drastic the temperature change is. Once our container is filled with liquid nitrogen, it entirely becomes this deep blue. You can even see the liquid nitrogen boiling away on the surface. Whereas in real life, or with a regular camera, we can't see through the gas at all. But we are here to levitate an object, so what does liquid nitrogen have to do with magnetic levitation? Because you can make magnets levitate without it right now. And to demonstrate this, I'm going to use Ink's levitating rings, which is a fun product that Michael, Kevin, and I made for the Curiosity Box. There's a link down there in the store if you want to get your own, or you can use any two magnets that you have at home. Now, let me show you how this works. If these two magnets have like poles facing each other, they repel each other. It is the same principle for how maglev trains work. And the opposite occurs if we flip the magnets around. They're attracted to each other. But what we're doing here is not regular magnetic levitation or maglev. It's superconducting maglev, which is different. First of all, let's discuss superconductors. A superconductor is a material that exhibits two incredible properties when it is cooled below a so-called critical temperature. The first is that they have zero electrical resistance. But more important for our purposes is the Meissner effect, which causes a superconductor to completely expel magnetic fields when they enter their superconducting state. What that means is that a superconducting material will actually levitate over a magnet.
I think audio is not working somehow.
Put on top of a stainless steel core and covered by a protective layer of silver and aluminum. And when I say a tiny sliver, it really is. It's just 3 microns thick, 30 times smaller than the thickness of a human hair. And if I were to put a magnet next to it, well, nothing happens because it will only levitate when it's below that critical temperature, which is why I drowned it in liquid nitrogen. One of the most amazing things about superconducting levitation is what you see here. Not only does the disk hover above the track, but it can hover below it as well. In fact, we can shape the track any way we want, and the disc zooms along at exactly the same height, no matter its orientation, with no friction or resistance. That's due to a phenomenon called flux pinning or quantum locking. Basically, while the Meissner effect means that any superconductor will expel magnetic fields, if you intentionally introduce some imperfections into that material, then a little bit of the field can penetrate it in discrete quantities called flux tubes. Inside each of the tubes, essentially a tiny bit of magnetic field gets trapped inside the superconductor, pinning it in place. And what I mean by that is that our superconductor, our disk, is quantum locked to the magnetic field generated by this track. That's what allows our disk to go back and forth and upside down without falling off or flying off either end. It also is what allows us to minutely adjust the superconductor's orientation. Now, to be entirely honest with you, I don't know how to end this episode, so here is some more cool levitation footage set to the song Flower Duet from Delibes' opera Lakme. And as always, thanks for watching.
This is from my side.
Very well done, Nitin. Very well done. Very consistent. Very well done. May we see your face? Nitin? May we see your face, Nitin? Very well done. Very good. We are not getting you, Nitin. You are muted.
Thank you, ma'am.
Yes. Nitin, still it seems you are muted.
This episode was made.
I'm using two devices, that's why it is happening.
Yes, I was thinking so. For presentation, you have used the other device. Thank you so much, Nitin. Do you think, was it worth preparing yourself and presenting the same thing? Do you think it is worth?
Yes, ma'am, it was.
Very nice. You are from Ahmedabad, Nitin?
No, ma'am, I'm from Bharuch.
You are from Bharuch.
Yes, ma'am.
Okay, fine. Students, rest of the students, I hope everybody are all presentation would be. I'm talking about content. અને જે રીતે નીતિને શરૂ કર્યું હતું, that was superb. He has started with conductor, semiconductor and superconductor. Students, are you able to get the point?
Yes, ma'am.
જે નીતિને પ્રેઝન્ટ કર્યું એ બધાને સમજ પડી?
Yes.
Yes,
Yes,
ma'am.
ma'am.
Yes. Nitin, just I have recorded your session also. Do you want the recording? Do you know I have started recording?
Yes, ma'am.
How do you come to know?
And there is a red dot at upper end.
Yes, it will be available. It will be available.